You'll hear in almost every Pluto video that a heavy bomber burned over 2,000 gallons of fuel in a single mission. Proof the Allies desperately needed an undersea pipeline to France. But here's the problem. Those bombers flew from England. Their fuel never needed to cross the Channel. So what was Pluto actually for? Let's deal with the bomber claim first, because it tells you everything about whether the person making the video actually thought about what they were saying. The numbers are real. A B-17 Flying Fortress burned roughly 200 gallons of aviation gasoline per hour. A deep penetration raid into Germany, 8 to 10 hours, takeoff to touchdown, could consume 1,600 to 2,000 gallons in a single sortie. The B-24 Liberator was thirstier still, around 220 gallons per hour at cruise. The Avro Lancaster carried over 2,000 imperial gallons and burned through most of it on a long run to Berlin. So the arithmetic checks out. The geography doesn't. Every single one of those heavy bombers took off from England and landed back in England. The United States 8th Air Force operated from bases across East Anglia: Thorpe Abbotts in Norfolk, Framlingham and Horham in Suffolk, Kimbolton in Northamptonshire, Bassingbourn in Cambridgeshire, all on English soil. RAF Bomber Command stretched from Yorkshire through Nottinghamshire and Lincolnshire. The aviation fuel that fed these fleets was refined, shipped, stored and pumped into aircraft on the British side of the English Channel. Not a single gallon of bomber fuel ever needed to cross to France. Using bomber consumption to justify a cross-channel pipeline is like arguing London's water mains justify building a bridge to Calais. It's structurally incoherent. And it tells you, in 60 seconds flat, whether the person making the video understood what Pluto was actually designed to do. So what was it designed to do? Pluto, pipelines under the ocean, was built to feed the most relentless fuel consumer of the entire war, the ground campaign. By late August 1944, less than 3 months after Normandy, the Western Allies had landed over 2 million men and more than 400,000 vehicles on the continent. A Sherman tank drank roughly a gallon of fuel per mile across open country, more in combat. The hundreds of thousands of trucks, the GMC do.So being the workhorse, consumed fuel not just to advance the front, but to sustain the supply chain feeding it. And here's where logistics eats itself. The Red Ball Express, that round-the-clock truck convoy running from the Normandy beaches toward the advancing front between late August and mid-November 1944, was a logistical Ouroboros. Trucks delivering fuel to the front were themselves burning enormous quantities of fuel just to make the journey. At peak, the Red Ball operated roughly 6,000 trucks per day and consumed an estimated 300,000 gallons daily in its own operations. Fuel spent to deliver fuel. By autumn 1944, total Allied fuel consumption on the continent had surged past 800,000 gallons per day. General Patton's Third Army ground to a halt in early September, not because it ran out of Germans to fight, but because it ran out of petrol to chase them. That was the crisis Pluto was meant to solve. Not bombers that never left England, armies drowning in victory and dying of thirst at the same time. But before we get into whether Pluto actually solved that crisis, and I'll be honest with you about that, because some of you already suspect the answer, there's a name in this story that almost every Pluto documentary mentions and then immediately runs away from: Siemens. One of the 2 pipeline designs at the heart of Operation Pluto was called the HAIS pipe. That's an acronym: Hartley, Anglo-Iranian and Siemens, as in the German industrial giant headquartered in Berlin. The same Siemens that by 1944 was using forced labourers from Auschwitz and Ravensbrück in its factories. A German company building the Allies' secret pipeline. That sounds like quite the scandal, doesn't it? Except it isn't that story, not even close. The Siemens in HAIS was Siemens Brothers and Company Limited, a London firm established in 1858 by Carl Wilhelm Siemens, younger brother of Werner von Siemens, who'd founded the parent company in Berlin a decade earlier. Carl Wilhelm had arrived in England in 1843 as a young man of 20. And then he did something his family probably hadn't anticipated. He stayed. Became a naturalised British citizen in 1859. Anglicised his name to Sir Charles William Siemens. Married into English society. Was elected a Fellow of the Royal Society for his work on regenerative furnaces. Knighted by Queen Victoria in 1883. The company he built wasn't some satellite office, it was a colossus. By 1939, the Siemens Brothers works in Woolwich, southeast London, covered 35 acres and employed over 10,000 people. Walk through those factory gates on any given day, and you'd find one of the most specialised industrial operations in the world. A place where Victorian cable-making tradition had been refined over 8 decades into something no other firm in Britain could replicate. The core of the Woolwich operation was the cable shop. Submarine telegraph cables, the kind that carried messages under the Atlantic, the Mediterranean, the Indian Ocean, required a manufacturing process that was part precision engineering and part dark art. You started with a copper conductor at the centre. Around that went layers of gutta-percha insulation, applied hot, pressed smooth. Then came the lead sheathing, extruded in continuous lengths through hydraulic presses that forced molten lead around the core at enormous pressure, forming a seamless tube that would keep seawater out and the conductor dry at crushing ocean depths. Over that, helical wraps of steel tape for tensile strength. Then layers of jute yarn soaked in bituminous compound, wound on by machines that looked like enormous spinning wheels laid on their sides. Finally, an outer armouring of heavy steel wires, applied in a counter-helical pattern to resist the twisting forces that would try to unravel the cable as it sank through thousands of feet of water to the ocean floor. Every one of those steps demanded tolerances that would make a watchmaker anxious. A pinhole in the lead sheath meant seawater intrusion and cable failure. A weak spot in the armouring meant the cable could snap under its own weight during laying. Siemens Brothers had been getting this right since the 1860s. They'd laid cables across the Black Sea, through the Mediterranean, from Britain to India. The skills weren't theoretical. They lived in the hands of workers who'd learned from fathers and grandfathers on the same factory floor. And during the Blitz, they kept working. Woolwich sat in the heart of London's industrial southeast, prime target territory for the Luftwaffe. The arsenal next door took hit after hit. Bombs fell on residential streets surrounding the works. The night shift operated under blackout conditions. The enormous cable-wrapping machines turning in near darkness, the hiss of the lead presses masked by the thud of anti-aircraft guns from batteries along the Thames. Production didn't stop, couldn't stop. Britain's undersea communications depended on Woolwich, and so, though nobody outside a very tight circle knew it yet, would the invasion of Europe. And the critical corporate break had already happened long before. During the First World War, the British government sequestered Siemens Brothers and stripped away any residual German ownership. After the armistice, the company was sold entirely to British interests. By the 1930s, Siemens Brothers in Woolwich had no corporate relationship whatsoever with Siemens AG in Germany. They shared a surname and a founding family. Nothing else. Estranged relatives who happen to bear the same name. So picture this. April 1942. Arthur Clifford Hartley, chief engineer of the Anglo-Iranian Oil Company, walks into the Woolwich Works looking for someone who knows how to manufacture flexible submarine cable. He wasn't contracting with a German company, he was hiring the most experienced submarine cable maker in Britain. And what he asked them to do was beautifully lateral. Take everything you know about wrapping a telegraph conductor in waterproof, pressure-resistant, flexible armouring and do it around an empty tube instead. Make the cable hollow. Make it carry fuel. Meanwhile, across the North Sea, the parent, Siemens AG, was descending into the darkest chapter of its corporate history, exploiting enslaved people to arm the regime that had conquered Europe. One Siemens building pipelines to liberate the continent, another Siemens exploiting concentration camp labour to defend it. The shared name isn't a scandal, it's a tragedy of a family that ended up on opposite sides of a world war. The idea for Pluto had crystallised earlier that year when Admiral Lord Louis Mountbatten, then Chief of Combined Operations, raised a deceptively simple question. How do you guarantee fuel supply across the English Channel for an invasion force? Mountbatten approached Geoffrey Lloyd, the Secretary for Petroleum. Lloyd consulted the oil industry. It was Hartley who saw the answer. If submarine telegraph cables could be laid across ocean floors, why not a fuel pipeline? The technology for deploying flexible cables in deep water already existed, at Woolwich. The question was whether Siemens brothers could adapt it to carry liquid under pressure. They could. And what they built was remarkable. The HAIS pipe followed the submarine cable blueprint almost exactly, but with that one radical modification. No conductor at the centre, just a hollow 3-inch diameter lead tube. Around it went the familiar layers: steel tape wrapping, jute and bituminous compound, outer armouring of steel wire. The Woolwich presses that had extruded lead sheathing around copper conductors for decades now extruded the same sheathing around nothing but air. Same machines, same operators, fundamentally different purpose. The genius was the flexibility. A completed HAIS pipe could be coiled onto drums and unreeled across the seabed just as a telegraph cable would be, bending around obstacles, following the ocean floor's contours. A single length could stretch for dozens of miles without a joint. Fewer potential leak points, critical when you're laying pipe across tidal currents in wartime. Siemens Brothers' Woolwich Works had spent 80 years perfecting exactly this kind of manufacturing. The skills weren't invented for the war. They were inherited from the Victorian telegraph age and repurposed. The second design was the Hamel pipe, named after its developers H. A. Hammack and B. J. Ellis. Rigid steel, 3 inches in diameter, manufactured in short sections and welded into continuous lengths at a specially built factory at Tilbury on the Thames. The steel came from Stewart's and Lloyd's at their steelworks in Corby, Northamptonshire, a fact that town has never forgotten. Hamel was stronger under pressure than Hayes, but far less flexible, which created an extraordinary problem. How do you transport miles of rigid steel pipe across open water? The answer was one of the most audacious engineering contraptions of the entire war: the conundrum drum. Picture an enormous floating reel, roughly 30 feet in diameter, weighing hundreds of tons when fully loaded, around which welded steel pipe was wound like thread on a spool. These things were staggering. Each conundrum carried enough pipe for a single channel crossing, wound in tight coils under tremendous mechanical tension. Loading one took days. The pipe had to be fed onto the drum at precisely controlled speed, each wrap sitting flush against the last, because an uneven load would make the drum list dangerously once it hit the water. And hitting the water was when the real nightmare began. Tugs towed the conundrums across the channel. HMS Doris, HMS Doris II, and a flotilla of requisitioned vessels, while the drum rotated slowly, paying out pipe over the stern into the wake. The physics were brutal. A bobbin weighing hundreds of tons, floating in channel swells, doesn't want to travel in a straight line. It wants to roll, yaw, and swing. The tug crews had to maintain constant tension on the tow line, while matching their speed exactly to the drum's unspooling rate. Too fast, and the pipe could snap under tension. Too slow, and loops of slack pipe would pile on the seabed and kink. Communications between tug and drum tenders were limited to signal flags and shouted commands across heaving grey water. At night they worked by hooded lamp. The pipe sank to the seabed under its own weight as it paid out, which meant there was no way to guide it once it left the drum. If the tow drifted off course by even a few hundred yards, the pipe landed in the wrong place. And you couldn't exactly haul it back up and try again. Not miles of rigid steel sitting on a seabed 60 to 120 feet down in tidal currents. A giant cotton reel the size of a building, wallowing through grey channel swells, leaving a thin steel thread sinking into dark water behind it. Somebody had to think of this. Somebody had to convince the Admiralty it would work. And then somebody had to actually do it. Over and over, in waters that could go from glassy calm to force-sick swells in a single watch. Over the course of the war, roughly 710 miles of pipeline were laid beneath the English Channel, enough to stretch from London to Berlin and part way back. Thousands of workers drawn from the oil industry, the submarine cable trade at Siemens Brothers, the steel business at Corby, and the armed forces built something that had literally never been attempted. Piping fuel under an ocean, in under 2 years. Whatever you think of Pluto's operational record, and we're about to be very honest about that, the engineering ambition was extraordinary. Now for the part the title promised you. Pluto did not fuel D-Day. Not on the 6th of June 1944. Not in the first week. Not in the first month. On the morning Allied troops waded ashore at Omaha and Utah and Gold and Juneau and Sword, not a single drop of fuel was flowing through an undersea pipeline. The system wasn't ready. 2 routes were planned. Bambi, from Sandown on the Isle of Wight to Cherbourg, roughly 70 miles. Dumbo, from Dungeness on the Kent coast to Boulogne, roughly 30 miles. Bambi was supposed to come first because Cherbourg sat closer to the invasion beaches. But its timeline depended on the Allies capturing the port, which didn't happen until late June, and clearing it took weeks longer. The first Bambi line wasn't laid until the 12th of August 1944, more than 2 months after D-Day. In the meantime, every gallon of fuel reaching France arrived by brute force. Ship-to-shore tankers anchored offshore and pumped through flexible hoses. Barges ferried fuel up rivers. And everywhere, the jerry can. That elegant stackable 20-litre steel container the Allies had copied from a German design. Filled, stacked, trucked inland, emptied, trucked back, refilled. An endless cycle consuming manpower on a colossal scale. Pluto was supposed to make it obsolete. For the most critical months of the campaign, it contributed nothing at all. And when Bambi did come online, it failed. Not quietly, not gradually, spectacularly. The first lines laid toward Cherbourg began leaking almost immediately. The 70-mile crossing was a gauntlet. The English Channel's tidal range in the central basin can exceed 6 metres, generating currents that rip across the seabed at speeds that would knock a diver off their feet. These currents didn't just push against the pipe, they scoured the sand and gravel underneath it, creating unsupported spans where the pipe hung suspended between seabed ridges like a guitar string. Under pressure from the fuel inside and stress from its own weight, those unsupported sections flexed again, and snapped. One Bambi line failed within days of being laid. Engineers traced the break to a section where tidal action had shifted a gravel bank, dragging the pipe sideways across a rocky outcrop until the armouring wore through and the lead core ruptured. Another line developed multiple leaks along a 2-mile stretch where the seabed turned out to be far rougher than the pre-war hydrographic surveys had suggested. The surveys had been done in peacetime. Peacetime surveys don't account for the debris of war. Wrecked landing craft, dropped anchors, dumped munitions, sitting on the bottom and snagging anything that crossed them. Repair was almost impossible. You can't exactly send a plumber to a pipe lying on the seabed 60 feet down in water so murky you can't see your own hands. Divers could inspect short sections, but finding a leak in 70 miles of pipeline in strong current was like finding a needle in a haystack that was trying to sweep you away. Most of the time, the answer was to abandon the failed line and lay a new one, which meant burning through the finite stock of pipe that Siemens Brothers and the Tilbury factory had spent months manufacturing. During November 1944, the Cherbourg lines delivered only around 17,000 barrels. Pitiful, against daily requirements measured in hundreds of thousands of gallons. The Channel had won. 70 miles was too far, the seabed too hostile, the currents too savage. Bambi was largely a failure. If this were one of those lazy documentaries I mentioned at the start, this is where I'd pivot to some uplifting music and tell you Pluto was a triumph that won the war. I'm not going to do that. You deserve better, and the actual ending is more interesting. Dumbo was a genuinely different story. 30 miles instead of 70 meant fewer opportunities for pipe failure, weaker tidal forces, faster laying times. The Strait of Dover is narrow, shallow compared to the central channel, and its seabed, while far from friendly, lacked the extreme tidal scour that had destroyed the Bambi lines. The first Dumbo lines were operational by late October 1944. And by the 26th of that month, the system was deemed a success. Over the following months, 17 pipelines were laid across the Strait of Dover, and throughput climbed steadily. At peak capacity, Dumbo delivered roughly 3,000 long tons of fuel per day, approximately 1 million gallons. By VE Day on the 8th of May 1945, Pluto as a whole had pumped roughly 172 million imperial gallons to the continent. That's an enormous amount of fuel. But context matters. The 172 million gallons represented a significant but still minority share of total Allied fuel supply. The majority continued arriving by conventional tanker ships and barges through captured ports, Cherbourg, Antwerp, Marseille. Pluto was never the primary supply artery. It was a supplement. One detail most accounts miss. Pluto wasn't limited to a single fuel type. The system switched between motor transport gasoline, diesel and aviation spirit for tactical fighter bombers operating from captured airfields in France. The irony is sharp. The pipeline could carry aviation fuel, but for aircraft operating from French soil, not for heavy bombers sitting on English tarmac. The bomber fuel claim isn't just geographically wrong. It misunderstands the entire operational picture. So here's the honest verdict. As a system for fueling D-Day, Pluto was an unambiguous failure. It didn't exist when the invasion happened. As a solution to the logistics crisis of autumn 1944, Bambi was too late and too unreliable to make a meaningful difference. As a system for sustaining the final advance into Germany, Dumbo's 17 pipelines were delivering 1 million gallons a day and 172 million gallons by war's end, a genuinely significant contribution. Pluto was a qualified success that arrived too late to matter when it was needed most, recovered in its second attempt, and proved a concept nobody had dared try before. And that concept, pumping fuel under an ocean, is where this story stops being about the Second World War and starts being about everything since. Pluto was the first large-scale demonstration that subsea fuel pipelines were possible. The Haze pipe's core innovation, Siemens brothers' adaptation of submarine cable technology to create a flexible, continuous pipeline wound on drums and unreeled onto the ocean floor, was a proof of concept for every flexible subsea pipeline that followed. When the North Sea oil boom began in the late 1960s and 1970s, the engineering challenges were eerily familiar. How to manufacture pipe in continuous lengths. How to deploy it from surface vessels. How to cope with currents and hostile seabed conditions in water deeper, colder, and rougher than the English Channel. The conundrum drum. That magnificent floating reel unwinding Hamel pipe across the Strait of Dover was the direct ancestor of the pipe-laying reels aboard modern offshore construction vessels. Companies like Technip, Saipem and Subsea 7 operate ships today that are, in engineering principle, descendants of the tugs that towed conundrums through those grey swells in 1944. The flexible pipe technology pioneered in Siemens brothers' HAIS design found its most direct legacy in modern flexible risers and flow lines, the pipes connecting subsea wellheads to floating production platforms in deep water. Same fundamental philosophy, a composite structure of metallic and polymeric layers, flexible enough to accommodate vessel motion and seabed shifts, strong enough to contain high-pressure fluids. The scale is different. The materials have evolved enormously. But the core insight that submarine cable construction could carry fluids under pressure across an ocean floor was Hartley's insight, proven by Siemens brothers craftsmen at Woolwich 80 years ago. And Bambi's failure? That taught something too. Longer crossings required fundamentally different approaches than shorter ones. Tidal forces, seabed geology, and pipe material all interacted in ways pure calculations couldn't predict. Dumbo's success proved that with the right distance and conditions, subsea pipelines could deliver industrial-scale throughput reliably. Those lessons about the relationship between crossing distance, environmental forces, and pipeline integrity became foundational knowledge for offshore pipeline engineering. Every risk assessment written for a modern subsea pipeline implicitly draws on experience, tracing back to the engineers who watched their pipes snap in the currents off Cherbourg, and asked themselves why. Some of those pipes are still out there, by the way. Sections of Pluto pipelines sit in museums. Museums Victoria in Melbourne holds a section of HAIS pipe, and the South African National Museum of Military History in Johannesburg holds related material. Surviving pump station buildings still stand in the English countryside, strange fenced-off concrete buildings near Dungeness in Kent on the flat, windswept landscape of Romney Marsh. On the Isle of Wight, traces of the pump station at Sandown remain in the landscape. And at Shanklin Chine, a dedicated Pluto exhibition tells the story of the pipeline that ran from the island to Cherbourg. You can find them on Google Earth if you know where to look. In Corby, Northamptonshire, the Stewarts and Lloyds steelworks that rolled Hamel pipe has mostly gone, but the town remembers. These places always remember, long after the history books move on. The myth that Pluto fueled D-Day isn't just factually wrong, it's disrespectful to the engineers who built it, to the Siemens brothers workers at Woolwich who'd kept their cable presses running through the Blitz, the steel workers at Corby, the tug crews who nursed conundrum drums weighing hundreds of tons through channel swells at night by hooded lamp. Because it sets up an expectation the system was never designed to meet, and then implicitly judges it against that false standard. The real story is messier, more honest, and far more interesting than the version you've probably been told. A Victorian cable company's expertise repurposed for war. A first attempt that failed catastrophically in currents nobody fully understood. A second attempt that delivered 1 million gallons a day. And an engineering legacy that quietly shaped an entire industry for the next 80 years. That's the Pluto story worth telling. If you've got a personal connection, a grandparent who welded pipes at Tilbury, a family member who worked at the Woolwich Works, someone who grew up near one of those strange fenced buildings on the Kent coast, I'd genuinely love to hear about it. Drop it in the comments. The real history of Pluto lives in families and local landscapes, not in recycled scripts. And subscribe if you want more stories told this way, with the facts checked and the myths left where they belong.